it's simpler that way. And then f of x is going to be whatever it is, right? F f1, f2, f3, etc. As many values for f as there are values for x. And you can write that in memory pretty concisely. So the most general way of doing that is to have an array that contains all the values of x, and then another array that contains all the values of f. And then say, okay, the sample code x of I and f of I. As you go through I, x of I is going to be one of them, and f of I will be the corresponding f. If the x's have a certain regularity, for example, they start at 0, they take steps of 0.5, and they end at 5. Another way of saying that is that you start at 0, take steps of 0.5, and you take a certain number of steps. How many steps do you take? Well, you take 1, 2 for between 0 and 1, and then 1, 2, between 1, 2, and then the last thing is 4 and 4.5. So 0, 1, 2, 3, 4, right? You double that, you get 10, and then the 5 is by itself, so you've got 11 points. Another way of saying that is that you make 10 steps after the first one, right? As long as you keep your convention consistent, all of these things are pretty much interchangeable. So then you can write x as being, you have x is 0, you have step h, and a number, which is going to be the total number of points, say. All right. And then you just need f of I. You don't need x of I, because x of I, right? X of I, the imaginary x of I that doesn't exist in the computer, can be obtained by simply doing actually there's no comma here, it would be more like 2 points. X of I would be x0, right, plus h times I. So x of 0 is just x0 plus 0. So x of 0 is x0, x of 1 is x0 plus h, and so on, right? So you don't need to store everything. It's like it's redundant. You can compute it on the fly like this. But if you need particular values, you can store x and store f and do this. But now you have a function that's written as a set of values. The question is how do you use that as a function, right? If you have a new value of x, it's not. If you have a new value of x and you have the corresponding value in your array, then it's obvious. You just pick the corresponding value of f, right? So if x of 3 is equal to 5, and you're asking me what's f at 5, well, x of 3 is equal to 5, f of 3 is equal to 10, say. Well, f of 5 is equal to 10. So like written like this: f of 5 is equal to 10 if x of 3 equals 5 and f of 3 equals 10. Right? So you can go through your table, find the value, and give the corresponding value of f. But what if the x value you want is not in your table, right? Because you can't store all of them. Unless you're in a very specific case, you can't store all of them because that would be too much information, too much memory used. It would be probably slow. And usually when you store that function like that, when you have an actual expression for your function and you decide to write it like that, it's for speed. It's possible that this function it just comes from something else, like an experiment, something like that. So it's already in the table form. So then the question of how do you get from the table form, which is specific values, to an actual function that you can apply to anything, is useful not only if you want to represent functions on the computer like that in this like fancy way. It's also if you want to deal with real data that doesn't come from your program and is not given by an expression but by a table, you need to know how to do that. And let's just do it a simple way. All right, it's actually quite simple what you can do. Say you want to take into account all of the values in the table whenever you compute a new value in the output. To give in a new x, you want to use all the values of f at every point to figure out what would be the best fit of that. So you just pick polynomials. Could pick something else, but polynomials are nice in many cases, so let's use polynomials. So you need a polynomial that goes through all the points in your table of values, and then that polynomial you can evaluate, right? You can evaluate the polynomial and get a value, and that's what you wanted. It's a value that uses all of the values you have. Goes through all the points. So if you find an expression that goes through all the points and is a polynomial, you're good. Another expression is it should have the smallest degree that works. So if you have a very complicated polynomial that goes through all the points, that's bad. But if you have the smallest one, say a parabola or a line, it could be good. And these things I'm just going through very roughly at the beginning, and whenever we encounter an actual problem where we need more thought to be put. So all of these things are really crude, right? But when we encounter a problem that requires more sophistication, we'll just use more sophistication. For now, you have these values, you want to use all of them. The simplest polynomial will be the best, because you don't have any extra stuff, like if you have 2 points like this, it doesn't make sense that the function you predict is something like that. It makes sense that you have a line like that. That's the simplest thing. It has the advantage that there's only one line that goes through these 2 points, but there's infinitely many wiggles like that, right? So that wouldn't be very useful if you had like a method where on the points your function works, but outside of the points you have no guarantee that makes any kind of sense. So with these 3 ideas, I think we can do it. So okay, you want f at x, right? So you have 3 points. I'm going to do it for 3 points. It works for any number of points, but it's long to write, so we're going to have to use f of x 1 or x0. Okay, I'm going to go x0, x1, x2. Those will be my 3 x's. Okay, f of x0 is going to be a polynomial, 3 points. It's going to be a parabola, okay, in x. But a simple expression that will be so you want it to be equal to f of x0 when x is equal to x0, right? So let's put x minus x 1 times we need to put something here that's sensitive to the value of x, and when x is equal to x0, that thing will be equal to 1, right? In logic you sometimes write it like that. When x is equal to 0, that's equal to 1, otherwise it's not equal to 1. When x is equal to x0, it's not equal to x1 or x2. That's just our assumption that all the points are distinct, because otherwise what are you doing? Why did you give me twice the same point and maybe different values of f? That doesn't make sense. That's not a function. So you can clean it up before you give it to me, so that when I look at it, all points are distinct. So let's just assume that. Then x is not equal to x1 and x2. So x minus x1 over x0 minus x1, right? This, when x is equal to x0, it's going to be 1. But if x is not equal to 0, it's not going to be equal to 1. If x is not equal to x0, it's not going to be equal to 1. Alright, and the advantage is that when x is equal to x1, this goes to 0. Alright, so we'll get no contribution from this when x is equal to x1. And then you have to multiply by x minus x2 over x0 minus x2, right? For the same thing for x2. And then you can just add similar term for this, like that. X minus, and would be x0 over x1 minus x0.